Yes.
What do you have for us today? I'll go and mute
So
myself.
to tailor it more to beginners, we're gonna look at how Linux stores executable files, how these files will look like when they're actually executing as a process. We're gonna look at how Linux divides process memory into the different sections of memory and what they mean, what you can do with them. And then we're going to look at some exploits that you can do on processes. When I say exploits, in this case, I specifically mean, let's say you have a process running on your system. Maybe it's proprietary software. You want to change how it behaves. This is mostly what we'll focus on. Although the library I'll show you today, you can use it to make viruses, for instance, because you can inject your own code and then run it in another process. So if you do get execution on a foreign machine, you can inject into some process that you know. So yeah, that's basically what we'll do. And then I have just 3 demonstrations with the library I developed that kind of show you stuff like making an additional thread run in the parent, run in your target process, resolving function names in target processes. And there's something else, I forgot what it is. But the important thing with the demos is going to be that they're very stealthy. They're not very obvious. If somebody was to try to implement countermeasures here, it wouldn't just be. It wouldn't be very simple to get around it because all of these methods kind of take into account what the other person could be doing to prevent it. So anyway, I guess we'll start with what the files look like on a typical system. I presented a talk on this like half a year ago. Well, it wasn't a talk; it was a presentation to 10 people, so not much different from here. But we'll just very quickly go over some basics. Let's see, any comments so far? So executables. If you guys know anything about Windows, or if you've done any reverse engineering or anything like that on Windows, you know that Windows uses the PE executable format. Linux doesn't use that. On Linux, we have the executable linkable format, or ELF. Tell you what, we can skip this for now. So this might be a bit much to take in, but we'll walk through it really, really slowly. So when you compile a program, the compiler, of course, is going to put it into a nice file that you can execute. And usually people, until you start to really look into it, people treat this file as just a black box that you execute and it does something for you. But it technically is just another data structure. It's just a very complicated data structure. So this is, for what we're doing today, this is more than enough of what we need to know. It starts with a little header and program header table. We don't really care much about that. The 4 that we're going to focus on today is the text, the RO data, the data, and the BSS. So if you guys have ever done assembly programming, this will be familiar to you. But if you haven't, I will introduce it quickly. So whenever you program anything, well, tell you what, no, let's take a step back. Whenever you program in a compiled language that compiles to native instructions, so not Python and not Java, it's things like C, C++, Go, Rust, so on and so forth. All of your instructions will be stored in one specific area of the file called the text area. Text stands for instructions. I'm not sure why they call it text, but that's just how it is. All of your how can I say this? So all of your data that is read, write, but not execute will be stored in data, but there is a lot of exceptions to this. If you God, this is very difficult to describe to people who may not have programmed in something like C, but with global, anytime you have any global variable, that will get treated differently from all other data in the program. So what do I mean by this? So to make it equivalent to Python, for instance, in Python you can define functions, and all of the variables in the function will go out of scope once the function concludes. This is not the case with global variables, which persist in scope across the entire program. Because of this, they get their own two sections in the ELF file format. The first is the RO data. This is read-only data. For example, you might have a program where you define a string like hello world that you print. The very string hello world will be stored in the RO data segment, or section rather, because we're still talking about the file format. Any uninitialized globals. So this doesn't quite exist in Python, but in C, for instance, you could define the variable x, and x would be an integer. If x is global, but it has no value by default, it'll go in the BSS section. So that's, in essence, the four sections: text, all of your program instructions; data, all non-global data; RO data, all read-only data; and BSS, all uninitialized global data. Tell you what, let's just move on. Is this important? Read elf. Not very. We're gonna skip over the headers because it's a bit too much at the moment. Yeah, that diagram's really all I wanted. So I'll show you an example program. Here, for example, we have OO CPP. So all we have is gonna print, and then it's gonna loop so that the process doesn't die. So the loop's here. It's gonna sleep for 10 seconds forever, and at the very beginning we print the uwu string. So if I compile that. Okay, now it's running. So in this window, I'm going to show you what's called the process maps. So actually, tell you what, I could really do with the presentation again. So let's have one last look at it before we continue. So I mentioned the text, RO data, and BSS sections. That's only when the file is on disk. When the file gets loaded and becomes a process, in a sense, so when it starts execution, these sections, they kind of, what's a good way to put it? They transform and they become individual memory segments. So how that works is, on a file, let's say you have instructions and you put bytes of instructions. It's also important to note that, actually, no, we'll get that later. So you only have 512 instructions of executable instructions. To load that into memory, you would need an entire page of memory. And operating systems typically divide memory page, typically use a page size of about 4 kilobytes, which means all of your 512 bytes of instructions will only go into the first 512 bytes of the page, leaving the rest of the page completely empty. Now, the question arises, well, why would you use an entire page to store so few instructions? Why don't you start storing read-only data, and so on? Why don't you store them in the same page? That's because modern operating systems implement a lot of countermeasures against exploits, specifically against C programs. So every single page has its own permissions associated with it. So, for example, your page that stores your instructions from the text section, it'll have read and execute permissions. You will not be able to write to it at runtime. This is good because you don't want you don't want an exploit modifying your program instructions as your program runs. If they find an exploit, it's very bad. So, because permissions can only be set at page granularity level, every single section from your ELF file has to go into its own page. So we will see that now. If we go back, went too far. Here. So the uwu program is running. Go here. We'll do read elf bold over. And I'll just scroll past. Ignore all of this. Most of this is not important. only here. So these here, this is very, what's the correct word? It's very intimidating to look at first, but I promise it's not so bad. So there's many different sections. We can ignore the vast majority. Most of them do not matter unless you're doing something very specific. But the ones that do matter is, as I've just shown you here, here's the text segment, right? Basically we have X for execute permissions. I think they all have read permissions, if I'm not mistaken. There is our read-only data. And then in other places, we will have... I'm not even... here's the BSS section, and here is the data section. So there's other sections, but don't worry about them. They'll only become important when you start doing something very specific. So here they are on disk. And other things that we can probably see is offset, align, and it doesn't tell you the size here, but it's okay. So if we now look at the process memory maps, so our process is running over here in an infinite loop. If we look at the process memory maps now, which Linux will expose under the proc file system, you can think of the proc file system as just the kernel's way of, the operating system's way of just letting you know what's going on with the process. So if you're an administrator, you can kind of look at the state of every single running process. So let's go to... for do less maps. So this is the process maps of this process. So as we just looked at, the ELF file, it had many sections, not just the text, data, and so on. But when our process, this is the only ones we're looking at the moment, when our process gets actually set to execute, most of the sections, they don't disappear, but they're used by the operating system to load the process, and you don't really encounter them much or often at all in the running process. So here, for instance, the names disappear. However, we can kind of tell what the function of the section is based on its permissions. So for example, this is read, no write, and execute. So because it's read and execute, we know that this is the text section. This is read write. So this is probably the data section, or BSS, one of the two. There are a few read-only sections. One of these will store uninitialized globals. So one of these will be the BSS section. And all of these processes here, sorry, not processes, all of these other sections here, they are from the libraries that the process loads. I'm not going to go into dynamic versus statically compiled processes. That's a bit far, but in essence, we only care about the ones that are associated with the process that we're running. The rest of these do not really matter for now. And then there's a few other things, stack and the heap. The stack is the storage that's local to your functions in a sense. So anytime you have a function that declares X, for instance, and when the function completes, when X goes out of scope, what that basically means is that the variable will no longer exist on the stack when the function completes. So that's why it's out of scope, because it ceases to exist. The heap is a bit different. You explicitly ask for storage on the heap, and it persists irrespective of which function is executing. That's probably the easiest way to describe it. It's quite complicated, but we don't have to go into it at the moment. So that's a rundown on. That's a very quick rundown on how on executable file formats and how they translate into running processes. And I'm going to take some questions now because I'm sure all of you are very confused. So any questions at all? I really don't mind. You can ask me like 50 questions. So we can walk through it slowly. It's all right.
Yeah, I wouldn't worry too much in regards to having to explain everything to a novice, because this is not novice material.
Yeah.
Again,
Yeah.
if you guys are watching the YouTube video after the fact, go to our Discord server, download the launcher. There is Wonder. Wonder will teach you. We have our operating system module out. Wonder will teach you about operating systems, about Linux, so you can kind of understand how an operating system works fundamentally, so you're able to then understand what the hell is being talked about right now. Because it's very much operating system specific.
I remember when I went to slide 3. I do remember. This is slide 3.
This is all gold. This is great stuff right here. 100%. This is putting a big smile on my face.
Yes, thank you. So slide 3. See this is like executable exploitation. So it's local to your. It's just the program that's local on your system. So we're on Linux, and the staff used to see all of the. To examine ELF files, you use the read ELF utility. It will process the ELF headers for you and tell you basically like the meta information about an executable, like where all the sections start, what the sizes of each section are. And then once the program is actually running, to see it in memory, you have to go to the proc directory on the file system. Linux is quite special in a sense because unlike Windows, the file system itself can be used to get information about, well, everything about running programs, about devices, so on and so forth.
There, if you go, there should be a chat available to you. If not, I'll link you to it for Wonder, access to Wonder for our operating system module. If you ask Wonder about any of these questions that you have after the fact or anything he's explaining here after the fact, Wonder will at depth educate you from the ground up, so you will become a master at all of this also.
So before we look into the library, let's consider some when you'd actually want to mess with running processes, or when you would want to do any of this. I think the big obvious use case, which I think a lot of people in this Discord are interested in, is making cheats for games. This is precisely how you make cheats for games. Maybe not Valorant because their anti-cheat is so aggressive, but for everything else, this is absolutely what you would do. This is also how you write malware. For example, specifically viruses, which tend to inject their own code into existing processes. Viruses will do exactly this. They will exploit running processes or inject themselves into the ELF files of programs that they target. So that's just a few use cases. I'm sure there is others, but that's the two major ones. So now, let's see. Okay. So now we're going to take a look at a library I wrote called libpwu. It's a good name. As you can see, this is the documentation for the library. We've got quite a few. It documents every function. What libpwu does is, well, I'll tell you what, let's just see the main page. libpwu automates a bunch of tasks that you would typically want to perform whenever you're exploiting a process. So things like you found a function that you're interested in and you'd like to run your code when that function runs. libpwu allows you to hook that function. It automates payload injection and mutation. So you want to run some custom code, libpwu will inject your code into the process and it'll allow you to mutate it before you inject it. You'd want to mutate it to correct any offsets for any jumps or anything else really. For defeating ASLR, it's necessary. Cave enumeration. So what caves are, as we spoke previously. As we said previously, if you only have 500 bytes of instructions, but you need a full page to store those instructions, you're going to have, in this case, 3.5 kilobytes of unused page memory that has execute permissions. So you can inject your code into that quote-unquote cave, into that empty space, and then your code will be there. But if any anti-tampering system views the proc maps that we spoke about, these things for its own process, if my program examines the maps for itself, And if I inject a new region of memory, it'll appear here and it'll see it. And once it sees it, it'll know that the process is being tampered with. So if you inject into empty space, it'll defeat this countermeasure because it will not know that something was added to the process. It automates starting new threads. So, for example, let's say you have a process, it has 2 threads. One thread's used for networking, one thread's used for something else. You can inject your own 3rd thread that will run your own code, which of course then runs inside of this process, has access to all of its memory, can write directly to all of the memory in this process. It doesn't have to go ask the operating system for help. Again, that's very useful. Pattern searching, what you will often find is that when developers update a process, these things called offsets change. And when they change, any exploit that you wrote typically stops working because you will now be writing to incorrect memory addresses. To defeat this, people typically utilize pattern scanning, where to locate a function of interest, you essentially record kind of what it looks like in binary, in a sense. So if let's say this function has 20 instructions and these 20 instructions take up 60 bytes, you record these 60 bytes and then you scan all of memory for those 60 bytes to locate the function again after the update. So this lets you update your exploits once the executable is updated. Structured view of process memory. Well, for example here, guys, imagine having to programmatically look through all of this and try to work with this. It'll be very annoying. So this library will essentially create a bunch of structures for you that allow you to much more easily programmatically work with these process maps. And there's a bunch of quality of life utilities. So for a demo now, I have 3 small examples. This is directly from the documentation of libpwu. So one is creating a new thread inside the process. One is hooking a function. And one is resolving a symbol in the target process without making the process call without having the process call the dynamic linker, which is very important. Well, I'll explain what that means when we get there. So before we start, any questions?
What do you have a list of all operating systems you've tested this on?
This is just Linux. I mean, distribution-wise, I've tested it on Gentoo and Debian. So Debian obviously includes Mint, Ubuntu, so on, so all the popular ones. I think maybe Fedora it wouldn't work on, but I don't see why it wouldn't work on that.
Yeah, if you could test Fedora, because I mean that's Fedora, Red Hat are going to be the ones that are kind of gold standard in a lot of industries. And then antivirus systems, have you tested against any of those ones?
Well, I wrote this to cheat in games, so honestly I haven't yet. But I would not expect this to work. I'd expect that you'd have to go into the kernel to bypass it. I'm just asking to see. No, of course, yeah, that's fine. Because I mean, for example, let's say you're using this library as part of your virus, and you're you're attacking some containerized program. I mean, that's going to have stuff like ARP-armor, and it's going to sanitize all your system calls. So I think it'd have to be a very sophisticated process to get around that. So I wouldn't expect my library to be able to do that.
Okay. Yeah.
But for game hacking, this is more than sufficient.
Yeah. Because I'm looking at more not really for game stuff, but
yeah, of course. So let's see. Do we look at docs first, or do we look at examples first? Let's take a look at docs just so you guys get a vague idea of what we're doing before we begin. So the 2 main ones are intro and help. So because this is written in C, we implement our own vectors, which are pretty good. But of course, if you go there, I'll tell you what, this is too verbose. Let's not bother with that. I'll just explain everything as we go. So let's look at the first example, simple hook. That's probably the easiest example of the 3. So I'll show you the target process. Target, oops, wrong one, target.c. So all the target does, it's got 2 integers. It's got x and y. X is 4, y is 16. And all it does in a while loop is it adds the 2 numbers together and prints the result. So every time it runs, every 2 seconds, so once per loop, it should print out 20. The exploit called exec.c. Let's see if we can get this to be wider. There we go. This has a payload that is assembled. What it basically does, I wrote this a month ago, half a year ago, so you're gonna have to give me a second. But I'm pretty sure what this does is it'll holistically what this file will do is it'll find caves in the process. So as we said, caves, areas of executable memory that are, or not necessarily executable memory, just areas at the end of some region of memory that are empty that we can use. So it'll find caves, specifically executable caves that have permissions to execute code. It'll write the payload into said cave, and it'll redirect execution of our target program so that instead of running its add function, it'll run our own custom payloaded function. And what our payload does in this instance is it takes the result and it adds 3. So instead of printing 20, it'll print 23. So target offset, this is the target offset here, for example. Oh, there we go. The target offset here, for example, you'd have to reverse engineer to find the address of this function. But in essence, we know that from the beginning of the executable region, if you go in hexadecimal 687 bytes in, that's where the jump to the add numbers function takes place. So that's the jump that we have to patch. And then just briefly using the library, there's the introduction documentation kind of goes through this in more detail, but basically all we have to do is the main one really is to define this maps data structure, because this is the overarching data structure that kind of represents the process maps for our target process. Maps entry is it's one line from the file that we saw, so it's going to be one region. And then a few of these are just setting up. For instance, the Puppet info will be used to attach to the process. Caves will be for enumerating caves. This will be for injecting, so on and so forth. So this being C, we have, instead of having objects, we just have kind of the structure name plus a free prefix to initialize the structures. And another thing that's, God, do I go into this? I suppose I'll go into it. So let's say we have a region of memory that is read and execute, but we want to write to it. Well, by definition, it's read and execute, so we can't write to it. So the question is, well, how can we write a payload into this area of memory? And one way to do this is by using Linux has a system called mprotect, which will take any sequence of pages of memory and modify their permissions. So, for example, as we saw previously, I think, was it here? Yeah, as we saw here, for instance, we have the text segment, which has read and execute permissions. We can pass it this range of memory and to the system call and ask it to change the permissions to add write permissions. And if we check this again, it'll be read, write, execute. So, but the problem is that we can't call this on the behalf of another process. So it's the target process itself that has to call this. And the question is, well, how do you get the target process to call this in the first place? And to do this, we can use Linux's ptrace interface. So ptrace is kind of the debugging interface that's built into the kernel, which allows you to carry out programmatically conventional debugging tasks, like, for instance, stepping through the process, inspecting register state at breakpoints, so on and so forth. So what we can do, and this is what libpwu automates for you, which is what makes it quite great, is we have built-in functions like change region permissions. And if you look into the source code, how change region permissions works is it'll attach to the process, the target process. It'll save all of its registers, so instruction pointer, all registers, and so on. It'll then scan the process for a syscall instruction, which I believe is interrupt 80 in assembly, more formally. It'll change the instruction pointer to that syscall instruction, it'll then set up all registers to call the mprotect system call on this memory range of the region that we're interested in. So for example, we'll call mprotect on this region. So we set up the registers. So for example, in RAX would have this value, and then it may be RBX, we would have in hexadecimal 1000 to say that we want the next 1000 bytes. We will then use ptrace to execute just the system call itself and break when it exits the system call. And of course, after the system call, we now have these permissions will now be read, write, execute. We can write a payload in, set up the registers again to call mprotect again, remove the write permissions, and then restore state. So what I mean by restore state is we'll take those registers that we saved when we first interrupted the program, we'll restore them, put them back in the CPU, and let the program continue running. So now we just wrote our payload into the process, and as far as the process knows, nothing has happened. So this is in essence what we're doing. Row injection. I'll be honest, I'll have to consult my source code to remember how precisely this works. But it looks like it just injects into caves, which is good enough. And then it's just a bunch of cleanup. And so now I'll give a short demo. And also just to show you the payload, it's quite simple. You would just set up the stack and then add 3 to RAX before we return. So now, if I run the target, as you see, it's printing 20 every 2 seconds. Now if I run exec, it's now printing 23 each second. So that's the first demo. Sorry if I went through quite quickly. There's just like months of theory to go through, so I'm not sure how quickly I could cover it otherwise.
No, I don't really worry about it too much. This is, again, not really beginner-friendly stuff, so don't worry about explaining all the beginner 101 stuff.
Yeah, so let's take a look at another example. This time we're going to start a new thread in the target process. This is probably the most complicated example. This is also the one that took me the longest to implement. I was hitting my head against the concrete quite often. So the problem here is that, let's say you're trying to exploit a program that is single-threaded. And because it is single-threaded, it doesn't have Linux's pthreads library linked into the process. So you can't call any of the pthread functions to start a new thread because without yourself loading pthreads into the target process. But as we mentioned previously, if I load pthreads into the process, it'll appear here. There'll be another library like this, the same pthreads. And if the process ever inspects its own maps and sees pthreads, it'll know that something very strange is going on. It'll probably terminate and report that it's being tampered with. So we can't use pthreads directly. So we have to use the kind of the underlying interface that pthreads itself uses, which is clone system calls. The way Linux works and what makes it different from Windows in this instance is that every thread inside a process it's not a multi-threaded processes are actually a collection of processes, of standalone processes that share virtual memory. So and the things like signal handlers and so on. So as far as the kernel is concerned, there is no such thing as multi-threaded programs. It's every program just has, they're all just what's called in the kernel as tasks. So a task you can think is one thread of execution. And they just happen to be grouped into groups that share things like virtual memory, exception handlers, signal handlers, and so on and so forth. So because of that, the system call to start a new process and to start a new thread is the same system call. It's the clone system call. So let's take a look at the code here. Because I need to remind myself how I've done this. I remember vaguely, but let's expand this. I think we have a bit of a mix-up with space and tabs. That doesn't matter. So this is the other thing with Linux. On Windows, when you request a new thread to be made, when you request an operating system for a new thread, it'll allocate the stack for you. It'll do all of this stuff for you, because on Windows, you tend to call the Win32 API, or maybe even one of the high level ones, which will take care of all of this for you. Linux doesn't. Linux's pthreads library does this, but we're not using pthreads. We're using the system calls directly, and because of this, we have to do things like allocate our own stack for our thread. So in this example, I believe we are allocating our own stack. However, there's nothing stopping you from using a cave that you found in a read and write area and using that as a stack instead. That works perfectly well, and that'll be less detectable. So as always, we initialize the maps data structure, which will summarize all of this programmatically. We find the process ID by the name, because we pass it like target, for instance. We pass the name of the process, not the PID, so we'll find the PID for us. We open its memory. We read all the maps. And then this syscall here. Also ignore the tabbing. The tabbing is incorrect. This will find a syscall instruction. So in assembly interrupt 80, it'll find that in the target process. We then attach and change region permissions so that we can inject a payload. Now this is the really interesting part here, because the way pthreads works is, or the way Linux works underneath, and this is what makes this probably the most complicated demo we'll do today. Whenever if a thread is executing and my debugger wants it to stop at a specific instruction, you'll typically ask the processor to send that process a signal that it can't block, specifically when it reaches that instruction. So it'll be a hardware interrupt that then immediately gets handled. But what this means, let's say we have a thread that we just paused. And let's say we tell this thread, like we've done in a previous example, execute the system call and then break again once you exit the system call. This only works for the current thread. And for the clone example, the thread that we're in right now, it'll enter the system call, but two threads will come out of the system call. Our thread that we're on and a new thread that we just created. And the problem we have, well, I had when implementing this, is that the new thread will not will not listen. It will not obey the debugger commands, in a sense. It will not break at the exit of the system call. It will just continue execution. And as you may have noticed, what we've done so far is we just found, here with change region perms, we're just looking for there we go, pop it find syscall. That's what I meant. We just find a random syscall instruction, right? But as you can imagine, if the thread exits at this random system call instruction and then continues execution onto the rest of the program, it's going to segfault, it's going to execute God knows what instructions. Its stack is going to be completely incorrect, and it's going to be a disaster, basically. So we can only use the system call whenever we're doing stuff that doesn't create new threads. Anytime we need to create new threads, we need to set up like a safety mat after the syscall instruction, so that the thread will not do anything stupid, or anything we don't intend it to do. So one solution for this, which is what our library does in this example, or what this example does with the library, is we I think it's, which function does this? Sorry, hang on a sec. I think it's going to be under start thread. It's going to be an internal implementation, internal to libpwu. We inject a very small payload into a cave, and this payload will begin with a syscall instruction, so that we can use that syscall instruction to create the new thread. And then at the end of the payload, or probably just immediately afterwards, we're going to have a jump, and this jump will go to the code that the thread is supposed to execute. So once the thread exits the clone, it'll immediately jump to the code that it's supposed to be running anyway, which means we don't have to worry about the thread. It's already set up completely fine, since it's going to have its own stack, which was set up before clone, and it's going to jump immediately to the code it's supposed to execute, which means we only have to clean up the parent thread that we used to create this thread. This is a really long-winded. Tell you what, Elijah, do you think it would be good to draw this out instead of just giving a 10-minute overview?
Say it again one more time.
Do you think it'd be good to draw this out? Like draw out specifically how you start new threads without threads?
I mean, I think drawing that's my favorite way of learning is visuals. Oh, yeah. But again, like if you think it's necessary to how your process works, then yes, draw it out. But if not, if it's something like, you can learn outside of this, then you can focus more on the code.
I think a lot of the implementation is you'd have to look at the source code of the library. So I'll give you guys a drawn out demo instead. So let's say this is the code of our program. And over here, we have the instruction for running a system call here. And let's say our process is currently over here. It'd be great if this had paint, yeah. So if our process right now is here, it's expecting to execute down this way. It's expecting to go down this way. So if we bring it over here, and it's going to execute down, it will not be good. It will not expect these instructions. The stack, which I don't know, let's say the stack. This is the stack. We all know the Stack Overflow icon. The stack will be completely wrong, and basically nothing good will come. It'll crash. It'll segfault. So what we can do is we can inject in a different area here. Let's say this is our thread code, right? We can inject our own instruction here, and let's call this bootstrap. Bootstrap, which has its own syscall instruction, right? Syscall. So once we move the main thread to here, and we make it call clone, and the clone comes out of the system call and runs down, our bootstrap code can have a jump to the beginning of the thread code, so that the thread never runs into all of these instructions here and messes everything up, but instead runs the thread code straight away. And then, as we've done in the previous example, we can just clean up the main thread, make it run all the way back, reset it to run all the way back to where it started, and then let the process go, detach from it as a debugger. And our normal thread, our default thread, will just keep running down this way. Our thread will run our code, and nothing will segfault, nothing will crash. This is probably way too advanced for like you guys, but it's alright. You can. I think if you review the code, it'll probably make a bit more sense. Or in like a year's time, perhaps. But yeah, so I'll give you the demo. So every thread has a thread ID. So over here, if I run our target is going to just print out the thread ID of the process. And now if we run our exploit, as you can see, there are now two threads. One is 1486, one is 1488. So we have two threads. And as you can see, there's twice as many lines being printed. So just like that, we injected another thread into the process. And then the final example that I'll give is very simple. This one is just for resolving symbols in the target. However, this is still very useful. So typically, usually on Linux, we have this thing called DLFCN. And DLFCN is what's called the dynamic linker. So as I showed you guys here, you see all these libraries, right? On disk, you only store your executable. However, when the process gets loaded, it's going to load all of these libraries that it needs. And the libraries that are needed are stored in the process. So this process stores the libraries that it needs. And then when the program gets loaded, all these libraries get loaded into its memory space so we can use them. So DLFCN is another one of these libraries. If you use it in your process, it'll appear just like these libraries here. What DLFCN does is it allows you to locate functions, specifically locate these libraries, locate functions inside of these libraries in your process. So if for some reason at runtime, when your process is running, it needs to for some reason load another library and use some new functions, which is something that you'll find malware commonly doing. You typically would use DLFCN. You'd pass the name of the function that you want to locate. It'll tell you the address, like I don't know, like say it's like here. It'll return the address, and then you can use this address to call the function. It doesn't really make much sense in Python, but in languages like C, you can very easily call a function just by its address. And however, but once again, to do this, you need to call it from the process itself. I can't run anything that this library provides for another process. The process itself has to run this function and get the address. So what this means is, if you're trying to exploit some process, and we want to find where the address is of some function within it, we need to link this typically. But as we said, linking it, very bad, because you're going to get a new section like this, and if a process scans its own process memory maps, it's going to see it and it's going to know it's being tampered with. So what's the alternative? Well, for example, here, we see that this program is linking user lib, so and so on, libm, right, .so.sticks. And this is on disk. So we can link this ourselves in our own process. And if we link this in our own process, this library will be identical to the library in the process. So in this text segment here, we can basically ask DLFCN to open this library in our own process, tell us the address of this function, and then see the offset from the beginning section here to the function, take the offset, and it's going to be exactly the same in our target process. So, the maps for our target process will be different, but we can apply the offsets to their maps to get the function address. So, if you look at the code for this exploit, oh god, all the spacing needs to be corrected, or tabbing rather. So we, as always, new maps data, get the process ID, open the memory, read the maps, all the setup's the same. But then this is what we do. We open the library in our own process. And then we resolve the symbol, in our case puts is just a very simple way to print text to screen, which is, for this example, it's sufficient. We resolve the symbol in our own process, it'll store the region that matched and the offset into that region. And this offset is going to be exactly the same in our target process. So after this, well, in this example actually ends here by just giving us the address in the target process. But in your own payload, you can use this address to call this function. And this is very important because, of course, it's very difficult to get by only using system calls. Realistically, you'd want to call library functions from your exploit. And using this, you can locate all of the functions that you're interested in using, and then use the mutation capabilities of libpwu to modify your payload before you load it in, so that it knows the addresses of all of these functions that you're interested in. And then basically, yeah, so to summarize, you can call any function you'd like as long as it's dynamically linked. Otherwise, you have to reverse engineer. You can start new threads. You can stealthily inject code into the target. And there's just a bunch of other utilities that make your life easier. So that's, as a summary, in essence, what my library provides. And yeah, I think that's it.
This is good. This is real good. I think what I'll do is I started recording. I should have started recording. Like, it's recording on YouTube, obviously, but I mean recording onto my disk for higher quality. I started like when you actually got into your library, so I'll probably cut that up and make that into a video that we'll post, and then on YouTube I'll download the video and make like the first part, because I see like it being split up into two videos. But overall, Uh, this was all really like 10 out of 10 stuff.
Oh, thank you.
Um,
Yeah.
I wonder. We can talk a little bit more afterwards, but I wonder if we can get something together for our next hack the flag,
Yeah, yeah,
where
sure.
people are given this library in order to complete some tasks, because that would
Yeah.
be fun.
Yeah, sure. That would work. Yeah, yeah. Um, yeah, I'm sure we can think of something. I can't think of anything immediately, but I'm sure it's possible.
Have you tried this in um, for the AWS Linux OS? I'm forgetting the name of it. The AMI or whatever they're called.
No, I haven't. I'm like a massive open source like boomer, so I avoid most cloud things. I use Akamai, but that's about it.
Okay. Akamai is good. Does Akamai have their own OS or they just have a default one they recommend
So
people use?
I think it's just default ones. I mean, I just run Debian for a Minecraft
Okay.
server, so yeah. But no, I think as far as the library goes, I'm pretty sure it's fairly reliable because I'm using it at the moment for a pretty big project, and I've not had any problems. I mean, I've had a few that I've patched basically, but from now on, I don't see anything else that's majorly wrong. Majorly wrong.
Well, I mean,
Um,
yeah, I'm just super interested because the possibilities for this are quite high, to be honest. Especially because I mean, a lot of people are running. Does this work in Docker containers? Have you tried that?
no, I haven't tried it. I mean, the problem with running it with any kind of like I'm sure in like quote unquote lab for learning it'll work, but any industry they're all going to sanitize all their system calls, and they will not allow like there's no way that they will allow a random process to call half the system calls that this requires. So I don't think so.
You would
I think
be
for
you'd be surprised.
yes, well, yeah, fair enough. I think
Where
realistically, to get it to bypass a good number of a number of these, you would probably need to like actually implement your own debugger in user space that doesn't trigger any of the syscall watch points, if that makes sense.
yeah,
So, which is possible, but it's like ridiculously tedious.
for that half, I mean, yeah, you don't really. This is enough work done. It's more so just cataloging like where it's
Yeah.
confirmed working. Because I mean, if it works, like for example, Akamai, when you spin up your Debian, you can definitely run it in a cloud
Mm.
resource from Akamai
Yeah.
in in Debian, and that's how pretty much most devs are spinning up their resources in cloud environments.
Mm.
I've never been on a project that uses anything like Fedora or Red Hat. They're using typically Ubuntu or Amazon based OS because most
Yeah.
most people still use AWS. So if it works in
Yeah.
there, I mean, you could do a lot if you're able to get initial access onto some cloud resources because
Yeah. Oh
then you
yeah.
can.
No. Yeah. I mean, for that, it's really good. Yeah. I mean, as I said, I wrote a pointer scanner which works insanely well because it automates like all of the tedious parts of it. And then yeah, I'm just gonna do. My plan in the near future, or like I say, relatively near future, because I've got so much stuff to do, is I want to like add some kernel stuff to it, if that makes sense, like some kernel modules that you can load that interact with the library, because just to bypass all of the like typical. I haven't
Yeah.
run into any countermeasures yet, but I'm sure as I do, it'd be really useful to have kernel bypasses for them.
Well, so I was talking to one of the supporters. I can't remember now, but I think it's just about time for Rootkit to have a proper Rootkit and Rootkit course. So if you're going to be doing
Yeah, yeah.
stuff like that, let me know, and I'm down to.
I can probably expand because my dissertation was working on like obfuscating eBPF rootkits, which are still they're still kernel rootkits, right? So, but there was a few things I didn't finish, so I could probably I don't know if you'd want to. It could be like a supplementary thing because I don't think you'd want to make eBPF the focus because it's so obscure. But it could definitely be like another rootkit thing
I
that you have
I don't care. I
because
don't care.
that's very new.
It's not for education, or it's for education. It's not for
Oh
practicality.
yeah,
If it
then
is
yeah,
practical, then that's a double whammy. But like, if people are
yeah,
able to spin up a known good VM in regards to exploitation or Docker containers or something to run all this. I mean, the rootkit, I don't know, would really work for Docker, but
Yeah. I mean, honestly, I don't see why it wouldn't work because this is all stuff that comes default pre-built into Linux, except maybe DLFC, and I'll have to take a look.
yeah, that, and then just if you ever do anything with containers.